Good morning, everyone. Hope everyone is doing well today. What we are going to cover today is we're going to pick up where we left off last day, and that is with encoding the configuration of the Rubik's Cube in terms of permutations and orientation vectors. So the idea is that pieces moved around on this puzzle, the corner pieces, the edge pieces, etc. They moved around, and wherever they've landed, they've also got an orientation associated with that. I'm just going to grab a puzzle here. There it is. It's a funny one in terms of how it's stickered. I can maybe mention more to you later if you want to know about how I've stickered this one. There's a method to the madness here. But the idea is that there's an edge piece. That's what we're calling our cubies. So that's an edge cubie. There's two stickers on it. There's a white sticker and a green sticker. The white's hard to see with the white plastic, and that lands somewhere on the puzzle. And wherever it lands, let me just rotate it here. Wherever it lands, it can either slide in like that, or it can slide in with its orientation reversed. And so we are encoding that information. Oops, I just put it in upside down, but we are encoding that information by saying, where does the cubie land? And there's also corner cubies as well. The corner cubies have the three colored stickers on them. As I said, this one's a funny colored one because it's they're all green, but I want to ask about this cube. After today, at the end of class today, certainly I'll answer your questions because we'll have all the information to understand what's so special about a cube like this. So we got our cubies. They land somewhere. Wherever they land, for corners, there's three different ways they can be oriented. Or for edges, there's two different ways they can be oriented. So that's how we split this up into permutations, where are the cubies, and orientation vectors. Once we know where they are, how have they been oriented? Have the edges been flipped over? Have the corners been rotated? Sure, yeah, okay. I'll make sure we get some time at the end for that one. The good news is we'll know the reason for this at the end of class. Well, at least we'll know the theory behind why I would even construct such a thing at the end of class. Okay, so we worked on a few examples. Let's do a couple more examples just to get familiar with how to write down this, what we call the position vector for so I called these, let's scroll back up. I call this the position vector, which is the 4 tuple. So it's the position vector consisting of the 2 permutation vectors and the 2 permutations and the 2 orientation vectors. And the order was corner, edge, corner, edge. So rho was corner permutation, sigma was edge permutation, V was corner orientation, W was edge orientation. So we go corners to edges at each stage. So let's go ahead and figure out what a move U corresponds to as a position vector. So these next two we'll go through relatively quickly. I went through quite methodically with the previous ones, but we'll go through relatively quickly with this one. So rho. So we got to figure out, where did the corners go? Well, this was just a twist of the up face. So the only corners that got moved were the upper 4 corners. And because this was a twist in the clockwise direction, you can see that the corner that starts in position 1 has now landed in position 2. And the corner that was in position 2, fill in a little bit more details here, so that will help when we are doing other examples. The corner that was in position 2, I look at the cube and I say, position 2, the corner that starts there in the solved state is, and I'll just read the colors around the vertex. It would have been blue. I'm essentially staring at the centers here. It would have been blue, orange, yellow. Those are the 3 corner colors, or the 3 colors that make up the corner piece that comes from position 2. So I say them as, I'm looking for the blue, orange, yellow corner piece. Blue, orange, yellow. Where's the blue, orange, yellow corner piece? Oh, it's sitting in position 3. Blue, orange, yellow corner piece is now in position 3. So the corner piece that did start in position 2, blue, orange, yellow, is now in position 3. What about the corner piece from position 3? That would have been blue, yellow, red. The blue, yellow, red corner piece from position 3 is now sitting in position 4. So corner piece whose home position is 3 is now sitting in position 4. And 4 is the blue, red, white corner piece. Blue, red, white is in now position 1. So this is our corresponding permutation of corners that has happened. What about edges? Well, edge piece 1 is the blue orange edge piece. That's the one in the back, the up back spot. It's the blue orange one. It is now sitting in position 2. And edge piece 2 is in position 3, and edge piece 3 is in position 4. Again, it does help. These numbers aren't there for the edge ones, but this is 1, 2, 3, and 4. Those are the edge positions, and then we just keep going around, sort of cycling our way around. 5 is in the back left, and then 6 is out on the side, and so on. So we just have to remember those numbers. Okay, and now we'll go ahead and do the orientation vectors. So we need V and W. V is the orientation of the corner pieces. So when I look at this, I say, well, what's the orientation on all my corner pieces? Well, the only corner pieces that are not in their home location with their home orientation are the 4 in the top. And they just got moved around the top layer in a cycle. Their blue stickers are all still in the top layer. So their blue stickers are the ones with the 0 number on them. And they're still in the primary faucet with the plus. So again, we'll scroll back up here. We're thinking about these two pictures. The numbers on the right-hand side, 0, 1, and 2, are the labels we've placed on the stickers themselves in relation to the primary faucet, which is the plus sign in their home location. And I just noticed that as I turn the up layer, it's just all those stickers on the top layer just move around, but they're still all under the plus signs. So it's zeros across the board for those. So this is the 0 vector. Similarly for the edges, the only edges that potentially got moved out of their home locations and orientations were the 4 edges in the top layer, but their blue stickers are still on top. Their blue stickers have 0 on them. They're still in the primary faucets. So that's a 0 as well. So what we would say is that this configuration of the puzzle, doing a U-move, the pieces have been permuted, but none of them have been reoriented. They're all in their original orientation. So no edges have been flipped, no corners have been twisted. It's kind of a funny way to say it because they're not in their home position. So it's really, have they been rotated? Have corners been rotated or not? But we are talking about them in a frame of reference. We are building our frame of reference in relation to those plus signs. So wherever a corner piece is, its 0 sticker is in the primary faucet. So it is not twisted. So here's an example of a configuration where all the pieces have been purely oriented, or sorry, purely permuted, but none of them have been reoriented. They're all with their proper orientation. No flips, no twists. If we did a right move, like we did above, then some pieces did get flipped. Some pieces did get rotated. And you might say, well, there's really no difference between a right move and an up move. And that's true. There is no difference between a right move and an up move in some sense. But our way we defined our primary faucets does not reflect the symmetry of the puzzle in terms of the moves. So we gave priority to up and down layers. And so that's why we're seeing that when you do a right move, some pieces get flipped and twisted, whereas you do an up move, there's no pieces that got flipped and twisted. And this is just all based on being relative to our frame of reference. So it's how we picked our frame of reference. It's just something we got to live with. If you don't want to live with it, then you can pick a different frame of reference. You're free to put the plus signs however you want, as long as it's just 1 per QB. But this one has its benefits that we give priority to the up and down layers. Let's have another look. So how about this this move sequence, which results in that configuration of the puzzle, we can go ahead and work out what our rows, our sigma, our v, and our w is. So rho in this case is how the corners got permuted. Did they get permuted? Well, corner piece 1 is in spot 1, so it's in its proper location. Corner piece 2 is blue, orange, yellow. Blue, orange, yellow is now in position 4. Blue, orange, yellow is now in position 4. So because blue, orange, yellow is in position 4, it means 2 has gone to 4. And where has corner QB4 gone? Corner QB4 is blue, red, white. That's now in position 3. Blue, red, white is in position 3. And corner QB3, which is blue, yellow, red, that is now in position 2. So there's been a 3 cycle happening on the corner pieces. And this is why we've referred to this as a 3 cycle, because that is a 3 cycle in terms of the corner QBs. We haven't worried about orientation yet. How about the edge permutation? Well, all the edges are back in their original spots. So that's the identity. How about the orientation vectors? Well, corner QB1 is properly oriented. It's corner QB2, 3, and 4 that we have to figure out the orientation of. 5, 6, and 7. 5, 6, and 7, and 8 are all in their proper orientation in their home locations. So they're unoriented, they're not twisted. So how about 2, 3, and 4? So let's look at the 2 spot. Corner QB2, that's currently sitting in position 4. So I look over at position 4, and I think what number is on the orange sticker, because that orange sticker is in the primary faucet. So what number is on the orange sticker? So corner QB2. Yep, this is corner QB2 right here. And I want to know what is the number that's on the orange sticker. So I remember that the blue is always a 0. And then we go clockwise around. So that would be a 1. And that would be a 2. So currently we have a 1. Yeah, so let's read clockwise around. Currently we have a 1 that's in that primary faucet. So that would be a 1 there. And how about corner QB3? Corner QB3 is currently in position 2. So I take a look at position 2. What is the number on the sticker in the primary faucet? So what's the number on the red sticker? Looking at position 2, because that's corner QB3. What number is on that red sticker? Yeah, that'll be a 2, because as we read around, it would go 0, 1, 2. So that's a 2. And then what number is on the final sticker? That's now corner QB4, which is currently, yeah, you got it, currently in position 3, blue stickers in that position, so it's a 0. And so that's a 0 up there. And then what about the edges? Well, the edges haven't moved at all. Nothing's happened with the edges. So this is still just a 0 vector. None of the edges have been flipped. So there's some examples of how we can compute these position vectors. Now, what I'd like to do is I'd like to make an observation. You know, as we were doing this, we did that last one with the orientation of the corners. We got the 1, we got the 2, and then we had to decide on that last one. If this is a solvable configuration, that means no one messed around with it and took it apart and reassembled it in a way that couldn't be solved. If it's solvable, then we actually didn't really need to glance on that at that last cube to figure out it was in the 0 position, that it was properly oriented, because there's a way to get this from these orientation vectors. And so that's what I want to talk about next, that what are the criteria we have on these permutations and orientation vectors that guarantee a solvable cube. So there's a couple more examples. We can come back and do these examples, but I want to get to this solvability criteria. So not every four tuple turns out to correspond to a solvable configuration. For example, we've seen that if we flip a single edge, then that's not solvable. So a single edge, let's say it's the second edge QB, the one in the upright position, then this would be what the corresponding position vector would look like. Nothing would be permuted. Edges and corners are back where they started from, so identity, identity. Corners haven't been twisted at all, so that's just a zero vector. Only one edge got flipped, the second one, so there's a 1 in the second position and zeros everywhere else. And we know that this isn't a solvable configuration because you can't flip a single edge. So that means considering the collection of all possible four tuples might be interesting because it's only a sub-collection of those, a subset of those that are actually solvable. So that's what I form here. I form what I call RC3 star with the star up there. And this is called the illegal cube group. In other words, it's the set of all possible configurations of the Rubik's Cube where the cube may have been taken apart and reassembled. These are not the solvable ones. These are the solvable ones plus all the other ways you can reassemble it. So this is called the illegal cube group, or what is often referred to as the assembly group, meaning it just represents all the ways you can assemble it. So these would be assembly instructions, rho, sigma, v, w. If someone gave you a four tuple and said, assemble the cube in this way, rho and sigma would tell you where the cubies go. V and W would tell you how to twist or rotate them when they get to that position. So those can be assembly instructions. Not all of them are going to be solvable. Not all of them, when you assemble them in that way, can you twist back and get the solved cube. Just like with the 15 puzzle, you can dump all the tiles out, and when you put them back into the tray, some configurations aren't solvable. And with the 15 puzzle, we get down to two states. We either solve it, or we get down to where the 15 and the 14 have swapped positions. So with the 15 puzzle, the illegal 15 group, or the assembly configurations, split up into two types, those that are solvable and those that aren't. And there's half of one type as there are of the other. So the whole collection splits into half. There's half of them are solvable and the other half go to the 14, 15 swapped. That's what we want to do with the Rubik's Cube. When we reassemble it, we'd like to know, is it solvable? And if it's not, how close to the solved state are we going to get if we go ahead and try to solve it? So this requires us to have a solvability criteria for the cube. And here's our solvability criteria. With that position vector, rho, sigma, VW, it corresponds to a legal configuration of Rubik's Cube, or in other words, something you could solve, if we have the following three conditions satisfied. The parity of the permutation of rho is the parity of the permutation of sigma. So rho and sigma have same parity. Remember, sine was just sine of an even permutation is 1, and sine of an odd permutation is -1. That's what the sine function is. It's just a way to assign a number to the parity. So this says they have to have the same parity. The next part says that the sum of the orientations of the corners has to be 0 modulo 3. So it's got to be a multiple of 3. When you add up those components of the v vector, it's got to be a multiple of 3. And when you add up the components of the w vector, it's got to be a multiple of 2. In other words, this tells us, as I've written down below, permutations of edges and permutations of corners have the same parity. The number of clockwise corner twists is equal to the number of counterclockwise corner twists, mod 3. And the edge flips occur in pairs. We will prove this theorem. Actually, I've written the proof down below. I'll walk through the sketch of how you would go ahead and prove this. And so we'll catch all the details of how you would do it. Yeah, so good question. And so no surprise, it's related to the fact that we know 4 moves. Corner 3 cycles, edge 3 cycles, corner twists, edge flips. We know 4 moves, and that's all we need in order to prove this theorem. So edge flips have to occur in pairs. Corner twists have to occur in 3s in the same direction or in pairs if they're rotated in opposite directions. That's what this is telling us. So if I scroll back up, let's just take a look at these ones. The identity, well, that obviously satisfies it because the identity is equal to the identity and they have the same parity. The sum of the components of V is 0. The sum of the components of W is 0. The next one, this one's a little bit more interesting because if I sum the VI's, I get 1 plus 2 plus 2 plus 1, which is 6, which is congruent to 0 mod 3. So that tells me that it's, at least in terms of orientation of the corners, that they have been twisted properly to be solvable. And then the sum of the WI's is 1 plus 2, 1, 1, 1, 1. So there's 4 1s. So the sum is 4, which is 0 mod 2. So an even number of 1s. And this one's telling us that they have been twisted in pairs. There's a clockwise, counterclockwise pairing that happens. 2 corners have been, two corners in a pair have counterclockwise, clockwise, which we can fix. And another 2 have a clockwise, counterclockwise pairing, which we can fix. Here's an example where, oh, maybe I should have said here, these are both odd. Here, these are both odd permutations. And again, we get that the sum of the VI's and the WI's are 0. They're outright 0 here, not even in terms of reduction modulo 3 or 2. They're just outright 0. And this also tells me why I know that should have been a 0 here, because 1 plus 2 is divisible by 3 already. So that last number has to be 0 in order for that sum criteria to work out. The sum of the VI's is 3, which is 0 mod 3. Okay, so that also tells us one additional thing, which is a fact that we're going to exploit quite a bit, is that if I know how, I'm going to talk about it in terms of this, I knew these values. I knew 7 of the 8 orientations. And that 8th one, I had to, it was forced upon me. There was just no other choice for that 8th orientation. If the sum of the 7 orientation numbers is divisible by 3, then that 8th one has to be 0. There's just no other choice. So the orientation of the last corner is determined by the prior 7 orientations. Exactly. It's kind of like the applet forcing the 14 and the 15. Once you know the orientations of 7, the 8th one is forced upon you. And same with the edges. Once you know the 11 of the edges and how they've been flipped, the 12th one is forced upon you if you want it to be solvable. If you want it to be not solvable, then you take the opposite of the one that's going to force it to be solvable. So if you're really trying to be devious to your friend's Rubik's Cube and take it apart and reassemble it, then you probably want to reassemble it in such a way that it's not solvable, in which case you do want to take one of those other choices that forces it not to be solvable. All right, so this is just a few of the conclusions that we get from this theorem. Corollary 20.2.2, impossible configurations. So these are all the ones we've observed before, and a couple that we couldn't do by hand, but we did with Sage. Now we can get them all by hand from this theorem. So exactly 2 edge cubies are swapped. That's impossible, because if 2 edge cubies are swapped, that's an odd permutation of the edges, but the corner cubies are all where they're started. So that would be an even permutation of the corners. And those parities are different. The edges and the corners have opposite parity as permutations. So you can't swap exactly 2 corner cubies. In other words, you can't have the edges oddly permuted while the corners are evenly permuted, and vice versa. And that's part B. You can't have two corner QBs swapped, because that would mean the corners are. So all of these mean just as the basic, right? I can swap two corner QBs, but I also have to do an odd permutation of the edges as well. But here I'm saying that, can we have a move that is just purely swaps two corner QBs, leaves everything else where they started? And the answer is no, because that would be an odd permutation of corners, while an identity or an even permutation on the edges. Could we have one edge QB flipped? So take an edge QB and flip it over. And the answer is no, because that would violate B, the sum of the orientation numbers of the edges wouldn't be 0 mod 3, it would be 1 mod 3. Can we have exactly, or sorry, sorry, I looked at B, I meant to say C for the edge ones. So again, here, can we have one edge QB flipped? The answer is no, because the sum has to be 0 mod 2. So I'd need an even number of edges flipped. How about the next one? Can we have exactly one corner QB twisted? And the answer would be no, because that means one of the W's would be either 1 or 2, depending on which way you twisted it, and all the other ones would be 0, and the sum wouldn't be 0 mod 3. Did I say W? I meant to say V. One of the V's would be. Sorry, I keep looking up and flipping the order. So the V's are the corners. So can we have one corner QB twisted? No, because one of the V's would be 1 or 2, and the other ones would be 0. And that wouldn't be a sum of 0 mod 3. And we also get the additional statement that you can't have two corner QBs twisted in the same direction, because this would mean two of the VIs are 1, or two of the VIs are 2. And all the others would have to be 0. And if you had two of the VIs being 1 and everything else 0, the sum would be 2. Or if you had two of the VIs being 2 and the rest being 0, the sum would be 1. Because 2 plus 2 is 4, 4 mod 3 is 1. And so you wouldn't get the sum of the VIs being 0. So we get all of these for free just from that solvability criteria. So that's very powerful. The solvability criteria tells us a whole bunch of things that we knew before, but we knew for various different reasons with various different arguments, sometimes using SAGE. Now they all fall under one roof, and that is the solvability criteria. So let's go ahead and figure out what the size of the Rubik's Cube group is. So we know this from before. We used SAGE to compute it, 4.3 times 10 to the 19. We can now actually compute this ourselves. And so how are we going to prove this? The first thing we're going to do is we're going to observe that the illegal cube group, this one is easier to count, because the illegal cube group is just S8 cross S12 cross Z3 to the 8 cross Z2 to the 12. All right, that's what it is. It's the first component is a permutation on 8 objects. Second is a permutation on 12 objects. The third one is a vector where each of the components is either 0, 1, or 2. So it's in Z3. And that's there's 8 components, so that's why it's powered at 8. And then the last one, W, is a vector of length 12 with 0 or 1 as its component. So this becomes the size of that Cartesian product is just the size of the individual sets that make it up. And so it's the size of S8, sorry, I wrote S3, it's S8. That's 8 factorial times the size of S12, which is 12 factorial, times the size of Z3 to the 8. Well, there's 8 components. Each one of them have 3 choices. So that's 3 to the 8. And then Z2 to the 12 is a vector of length 12. Each component has 2 choices, 0 or 1. So that's 2 to the 12. So that's RC3 star. We want RC3. So the way we're going to get RC3 is we're going to notice that it actually, much like we did with the 15 puzzle, you dump all the tiles in, there's 16 factorial ways to do that. but only half of them are solvable. So you take 16 factorial, you divide by 2, and that's how many permutations you have or configurations you have of the 15 puzzle. Same thing we're going to do here. All the possible ways to reassemble the cube, which we just worked out above. And then we have to realize that not all of these are going to be solvable. In fact, for permutations, once I've permuted so I'm reassembling the cube, I put all the corners into place, and then I start putting the edges into place, permuting them around. Well, if the corners are evenly permuted, then the edges have to be evenly permuted. So I've cut in half my possible choices for the edge permutations. And so exactly half of the total possible permutations are possible to make it solvable. And this is because the sine of rho has to be equal to the sine of sigma. So I just cut in half the possible permutations I can use. What else do I have to divide by? Well, once I have put in 7 corner pieces and oriented them, the 8th corner piece, its orientation is forced upon me. So I don't have full flexibility. So for that 3 to the 8 that's sitting in the line above, that 3 to the 8, that tells me for that last position, I've got 3 choices, but I really don't. My orientation vector is completely determined by 7 of the values. So I have to divide by 3 because orientation of 7 corners determines the 8th. Determines the 8th corner's orientation. And similarly for the edges, the orientation of 11 edges determines the 12th. And so that's what we have to divide by. We have to divide by 2 times 3 times 2, or in other words, we divide by 12. So it's RC3 star divided by 12, or it's 8 factorial times 12 factorial divided by 2 times 3 to the 7 times 2 to the 11. And that's the end of our proof. So we've now figured out how big the Rubik's Cube group is by counting. This is a big step from what we've done before because we did this using a computer and that number was huge and you can't get a handle on, where did this number actually come from? It came from this. It came from figuring out how to reassemble the cube and then figuring out which positions are and orientations are restricted because of how previous things have been positioned or oriented. Now let's go ahead and prove the fundamental theorem of cubology. We're going to prove that that condition we have on the 4-tuple is the solvability criteria. So the way we're going to do this is we're just going to say we know 4 moves. That's all we really need to know. Corner 3 cycle, edge 3 cycle, corner twist, edge flip. The corner 3 cycle and the edge 3 cycle, that's going to help us deal with the rhos and sigmas, the permutations. The corner twists will help us deal with the vector v, and the edge flips are going to help us deal with the vector w. The way we're going to prove it is we're going to prove the 2 different directions. So the first direction, we're going to show that the conditions are satisfied for every legal configuration. So remember, there's 2 directions in the theorem. It says, if you're a legal configuration, then these are the conditions you have on your position vector. And conversely, if your position vector satisfies these 4 conditions, or 3 conditions, the parity one is joining 2 of those positions together. So if your position vector satisfies these 3 conditions, then it is necessarily a solvable configuration. So the first direction we're going to do is that we're going to show that solvable configuration is it must satisfy conditions A through C. So A through C are satisfied. So we're assuming at this point that our configuration is solvable, and then we're going to show that A through C are satisfied. So we start with the very first solvable configuration, that is the identity. The identity configuration is shown there in line 1. Rho, sigma are both the identity, V and W are both zeros, and that satisfies our 3 conditions. The permutations both are even, and the sum of the V's or the W's, they're zeros. Now let's extend and show that for any configuration, it is going to satisfy conditions A through C. And the way we do this is we just show that for each move, R, L, U, D, F, B, for all those 6 basic moves, when you do one of those moves, the configuration vector changes, but A through C remain invariant. So they stay the same. So if I have a configuration and I do a U move, then my permutations will change, but the fact that they have the same parity will not. They may both change from even to odd, or they both change from odd to even, or they may both go from evens to evens, or both go from odds to odds. It doesn't really matter. They both change in the same way. So if they were the same parity before, they're the same parity after. And similarly, if they satisfy the orientation sum condition then before you do a move, then they satisfy it after. And so that's all we're going to do here. Is we're just going to talk our way through it. But I'm checking that when I do one of the basic moves, that those conditions remain invariant. So they remain satisfied. So part A, they remain satisfied. The parity condition remains satisfied, since when you do a move, you simultaneously multiply rho and sigma by a 4 cycle. And so that simultaneously changes the parity of rho and sigma. They go from odds to evens or evens to odds, but if they both were the same parity before, they're both the same parity after. So parities remain invariant. When you do a move sequence, or a basic move, or even a sequence of them together, the parities of the permutations are the same. Both the corners and the edges have the same parity before the move than they do after the move. What about the corner orientations? Well, they remain satisfied, so the sum is still 0 mod 3, because, well, if you do a U or a D move, you don't change the orientations, because you haven't, the plus signs are all in the top or the bottom, so you don't change the orientation of any piece. But if you do an R, L, F, or a B, I'm just going to scroll back so we can look at the picture. I'm looking at this picture here. If we do an R, L, F, or a B, what happens? Well, I move a corner like this from one corner to the other. So whatever number was sitting in the primary faucet, when it lands in its new location, it's going to be the number that was here that is now in the primary faucet. Now think about what happens. This sticker on the side now becomes the one on the top. So that means we would have dropped by 1. So the orientation number would have dropped by 1. If the 0 was on the top, it's now a 2. Drop by 1 with this wrap. Or if a 2 was on the top, it's now a 1. Or if a 1 was on the top, it's now a 0. So it dropped by 1. But then if you follow what happens with all of the other ones, we get a decrease of 1, we get an increase. We get a decrease, and we get an increase. So 2 of them drop by 1, 2 of them jump by 1. And so they level out as a sum, because we've essentially added 1 a couple of times, and then we took 1 away a couple of times. And so they balance out. Same thing happens with the edges as well. So that's one of the nice things about the way we've built our frame of reference, is that we get these statements that follow. Simultaneously increase 2 components by 1 and decreases 2 components by 1. What about edges? Same thing happens. Only in this case, U, D, F, and B don't change W. You might say, well, how come we went from U and D not changing V to now F and a B not changing W? So I'll scroll back. rid of some of these markings. What happens when I do an F move? Well, I take this edge and I move it here. And so whatever number was under the plus sign is still the number under the plus sign wherever it went to. And similarly. So we're not changing the orientation vector for the edges at all. They don't change. These, when you do a front move, the numbers that are under the plus sign are still under the plus sign in their new location. The only ones that change are the right or the left moves. And that's where you get this, whatever number was under here, that move there. So it's the opposite that is now under the plus sign. So you get this you get this flipping happening. So two of them, well, actually all four of them flip. You can think of them, two of them go up, two of them go down, but it's either 0 or 1. So all four of them flip, and that doesn't change the sum in the end at all. So that's this one. And so that means if our configuration, rho sigma VW, satisfies conditions A through C, then every time I do a move on it, it still satisfies conditions A through C. So if it satisfies conditions, if a legal configuration, if I want to show that it satisfies conditions A through C, first I say, well, I can get to a legal configuration by a bunch of moves. So I start with the solve state, that satisfies conditions A through C. And then every time I do a move, it satisfies conditions A through C. So I do my move sequence till I get to that configuration, and it has to satisfy conditions A through C. And therefore, I can build up to it, and it has to satisfy conditions A through C. So if it's solvable, then it has to satisfy conditions A through C, because I can go down to the identity. So that's our conclusion. If it's legal, then these must be satisfied. So that's great. It means that if it's legal, then those have to be satisfied. But really, it's the converse we're interested in. If A through C are satisfied, then that's enough to show it's solvable. And so how are we going to do that? This is where our 4 moves come into play. So A through C are satisfied. So assume this is our configuration, and it satisfies A through C. Parity of rho, parity of sigma are the same. Some of the VIs are 0, mod 3. Some of the WIs is 0, mod 2. Then what I do is I say, well, if the parity of rho and sigma are the same, and they're both even, then I can solve each of them using 3 cycles. And I have 3 cycles available to me. So I could do 3 cycles to solve the corners and do 3 cycles to solve the edges. And so I can solve it if the corners and edges are evenly permuted. If they're not evenly permuted, so if the corners are oddly permuted, then the edges have to be oddly permuted because it satisfies condition A. They have to have the same parity. So since they're both oddly permuted, I can just do one move, like twist the right face. That multiplies each by a 4 cycles. So now they're both evenly permuted. And now, since they're both evenly permuted, I can solve them using 3 cycles. So that's step 1. Solve using 3 cycles. And so now we get down to a configuration that looks like this. Every piece is in its proper position. It's just it might be oriented improperly. But when I did all of those moves to fix the corner permutations and the edge permutations, bring them to the identity, properties A through C still remained true. So for this V prime, the sum is still 0 mod 3. And for W prime, the sum is still 0 mod 2. So maybe it helps to look at the second one for the W's first. If the sum of the W's is 0 mod 2, it means I've got an even number of edges flipped. So since W prime satisfies star, there are an even number of edges flipped. So just flip them in pairs. We have a move that does that, and so we can solve them. What about the corners? Since V prime satisfies B, it means that the sum is 0 mod 3. So it means that the number of clockwise twists equals the number of counterclockwise twists, modulo 3. So that means I could have 3 corners that are all twisted in the same direction, 3 of them all clockwise, or 3 of them all counterclockwise. So that I can either pair them up as opposites, or I get 3 that are all in the same direction. Either way, I can use my corner twisting move to solve them. So I can untwist pairs of them, and what's left maybe triple corner twists all in the same direction. So then I twist two of them as a pair, one in one direction, one in the opposite direction. That solves one, reverses the twist on the other one, and then pair it with the third one and fix them. So I can solve that using corner twists. And there we're done. So any configuration that satisfies A through C, we can solve it. We can use 3 cycles to fix the permutations, and then our pairwise corners or edge orientation moves to fix the rest. And so that's it. We've now got a solvability criteria for the cube. So the permutations have to be the same, and the sum of the corner orientation numbers has to be 0 mod 3, and the sum of the edge has to be 0 mod 4. Now here's the fun part. This is where you like to say, so suppose someone gives you a Rubik's Cube and they sort of are snickering a little bit, they give it to you, it's all messed up, and you look at it and you got a hunch that this isn't solvable. I'm guessing that they messed with it in some way. Can you detect that just by looking at it, maybe writing a few things down like we have? Can you detect that it's not solvable? And more to the point, can you actually fix it before you solve it? So for the 15 puzzle, you would look at it and you'd say, oh, the permutation of the 16 tiles is odd, but the empty space is an even spot, not solvable. I'll pry out any 2 pieces, swap their locations, drop them back in. Now I know it's solvable. So your friend hands you the 15 puzzle and it's messed up like that. You can look at it and go, oh, pick 2 pieces up, swap positions and go, now I can solve it. And then you go instead and solve it. And they'll be like, whoa, how'd you figure that out? How'd you know how to fix it beforehand? It's even better with the Rubik's Cube. How do you know how to fix it beforehand? That's what we're going to do now. So the way I'm going to build it up as an equivalence relation. So I'm going to say, we're going to build our equivalence relation on the assembly cube group. So this is all the different ways you can put the cube together. And I'm going to say 2 assembled cubes are equivalent under the legal cube group if you can take one to the other by just twisting the faces. So even though it's not solvable, perhaps, you can still twist the faces and get a whole bunch of other things that are related to it that aren't solvable. They're just related to it under cube moves. And so what I'd like to know is, what are these equivalence classes that I get under this relation? So for example, this equivalence relation partitions RC3 star into equivalence classes, basically the left cosets of RC3. How many are there? It's going to be RC3 star over RC3, or in other words, there's 12. So there's 12 different equivalence classes. So there's 12 different ways you can make, you can assemble the cubes, 12 different, inequivalent ways to assemble the cube up to twisting. One of them solvable, the other 11 are not. And in those other 11 cases, you can't ever take one in one situation to one in another, because they just sort of live in different orbits. They're sort of in different universes. You'd have to disassemble and reassemble to get to jump sort of what we call an orbit class there. So I'm going to figure out how we can characterize these 12 things, and we're doing it right here. I'm going to let this number Cijk denote the condition. So C is the letter for condition, and then Ijk are these values. So condition 110 would mean that the permutations are the same, parity, that's 1. J being 1 means that the sum of the orientation vectors of the corners is 1, not 0. And K being 0 means that the sum of the orientations of the edges is 0. So what I'm going to do is I'm just going to let these numbers be whatever they are. When you reassemble the cube, they're just whatever they are. I is 1 or -1, J is 0, 1 or 2, K is 0 or 1. For each collection of those numbers I, J, K, we're going to let Xijk be a configuration which satisfies those conditions. Those are going to be our representatives for those equivalence classes. And so here is our collection of representatives. So you read it as x1, 0, 0. The first 0 means that the parity of the two permutations is the same. The next 0 is what is the sum of the v's, and the next 0 is what is the sum of the w's. So this x100 is this solved cube. So this is what I'm calling the solved cube, x100. That's the solved cube. Well, what would the cube be, which is x negative 100? Well, that would be a cube where the parity of the permutations are opposite. That's the -1. But orientation of both the corners and the edges are fine. They both sum to 0. So this would be where you get a parity problem. The parity of the corners and the parity of the edges as permutations don't match. So here's a representative of that. The edges have been swapped. The corners being swapped would also be a representative in this class. But if I had the corners swapped, I could always reduce it down to a state where just the edges are swapped. So I can go from one to the other in that case. It would be like if I had the tiles 1 and 2 flipped on the 15 puzzle, well, I could always take that down to 14 and 15 being flipped. They'd be in the same class. And then we can just keep going along. I could have the case where we got a single edge flip. That would be denoted by 1, 0, 1. 1 because the permutations are the same, 0 because the orientation of the corners is good, but 1 because the orientation of the edges is out. There's one flip. And similarly, the next one is where we've got an edge swap and an edge flip. Or we could have a single corner twist, which is in the counterclockwise direction. Or we could have a counterclockwise corner twist and an edge swap that has happened. And you just run along the list. Basically, I'm taking these 3 conditions here, and I'm just saying, what happens if I let I, j, and k be all the different values they could possibly be? I is 1 or -1, j is 0, 1 or 2, k is 0 or 1. So there's 2 choices for I, 3 for j, 2 for k. So there's 12 possible mix and matchings there for I, j, and k. And these are what they give rise to. So if someone hands you a Rubik's Cube that's messed up and it's been tampered with in some way, disassembled and reassembled, what we're able to do is we're able to look at it, write down the rho, the sigma, the v, and the w, work out, are rho and sigma the same parity, yes or no? What is the sum of the v's? What is the sum of the w's? And whatever you get, you can look up on this chart and say, oh, it's this one because I got 1, 1, 1. Ah, that means to fix it, I will just grab an edge, flip it over, grab a corner, twist it clockwise 1 click, and then I can go ahead and solve the puzzle. And I can do that for any corner or any edge. So if someone hands you the puzzle, you're just like, not solvable, flip 1 edge, twist 1 corner, be like, now I can solve it. And then you go ahead and solve it. So you can do this detection. Next day, we'll do the last example, which is basically the last example. Sorry, I didn't time that very well. We're just over time, but this is the last example, and then you can detect. In fact, what I'll do is I'll put this in a video, this last one. I'll just make a little short 3-4 minute video, and that way you can have it for the long weekend to reference. It wouldn't take any more than 3 minutes to do this one. But I'll stop the recording now. And oops, I stopped the share. I meant to stop the recording. Stop.